Hello everyone. Good evening, guys. Good evening, everyone. To start the session, I would like to ask a question for SGD classifier. There are n iter, number of iterations as attribute. Okay, so in that case, when we create the object for SGD classifier, at that time we can initialize whatever value we want to give in n iterations. Stochastic gradient descent classifier, SGD classifier, when we access, we need to create the object first, right? Yes, while creating the object we specify all the parameters. Yes, this way. If it is the attribute of that class, what error is it throwing? Okay, in that case we need to make sure it is there. No attribute or invalid argument, something like that. Invalid argument or something like that. That's unexpected argument, that's invalid argument. So let me check if SGD has this n iterations. Okay, okay. What exactly is the problem you are solving? Okay, the file what I've shared. Just a sec. There should be an iteration, maps iteration, penalty L2 alpha, random state learning rate. This is an iteration number. I only see this one. Yes. Are you talking about this one? Because in SGD classifier, that is the only attribute about the iterations. We have max iter. Yes. Okay. And attributes. So, okay, in that case, if you want to access the attributes, then you need to do sgd dot n underscore iter. In that case, you need to do sgd dot. Okay, okay, yes. So, in that case, you need to do sgd dot n iter, and this will return us the information. Okay. Sgd dot n underscore iter, and it will return the information. Yeah, just a sec. Just a sec. Let me unmute. Yes, please.
Hello.
Yeah.
Yeah. Abhish, actually, it's regarding like in code. At at some point, you have mentioned like SDG classifier of an iterator equal to 10. The code which I've already shared in the chat, right? That's one.
Mm-hmm.
So now what happened is when if we do that, then an iterator is as per my understanding, like we are stopping at 10 iterations.
Mm-hmm.
This is what my understanding is. So when I give it as an attribute like SDC classifier as SGD classifier dot niter equal to 10, does that do the same activity as there in code, or does it act do in other way?
Okay. If we want to limit the number of iterations, basically, if we want to limit the overall, why exactly we use this parameter, I'll explain when we will do this stochastic gradient descent and other things in more detail. Let me give you a quick brief of what exactly is this. See, sometimes in order to optimize the loss, order to optimize the cost function, the iteration exceeds to more than enough number of times. So we limit the number of iterations. The maximum iteration should not exceed then some certain iterations in order to avoid the overfitting case. So in that case, we need to we need to restrict the iterations in stochastic gradient descent at a certain point. So for that, we use max iterations. Where it is, yeah, max iter.
Okay.
So this is how we limit the number of iteration that should be there.
Okay. Max iter we have to use. Okay. Fine.
Yeah,
Thank you. Thank you.
awesome. Okay, so we can start, guys. And long day to go. We have a lot of things to discuss today. Lot of interesting things, not just things. We have a lot of interesting things to discuss today. So, where's the pen? Yeah, here it is. We need to start with the classification algorithms, right? Now, in classification algorithms, we will go the same way. There are a bunch of algorithms. We'll try to discuss their mathematics and other things today. And later on, we will be talking about the codes and the business problems, right? So first of all, let's start with the very first classification algorithm, that is logistic regression. Okay. So logistic regression is also basically a classification algorithm, and this is used for binary classification only, right? It's for binary classification only, where the target variable is having only two classes, true or false, right? Or zero or one, anything, yes or no. Now we all know the equation of a straight line, y equals to mx plus c. Yes, guys? We all know the equation of a straight line, y equals to mx plus c. right? And in this equation, y is going to be an element of minus infinity to plus infinity, right? Y could be anything. There is nothing like y is going to be in a given range or something. The value of y could be anything, right? Perfect. But if we talk about the logistic regression, the actual y, the target variable, is going to be either 0 or 1, right? Yes, yes, the target variable is going to be either 0 and 1 only. But this predicted y equals to mx plus c is going to be minus infinity to plus infinity, and it's going to be a little difficult to map this predicted y to the actual y, right? We cannot actually carry out the insight as 0 and 1 from this equation, because it's going to be a continuous range from minus infinity to plus infinity. This can get any value. There is no certain no certain range, or no specific min and max where we are going to get the values. So we transform this y equals to mx plus c as sigmoid of y equals to 1 divided by 1 plus e raised to the power minus y, right? This is called sigmoid function. This is called sigmoid function, right? And now the sigmoid of y is always going to be an element between 0 to 1. It will be always between 0 to 1, right? This is a sigmoid. This is basically an activation function. The sigmoid is basically an activation function, and this will transform any continuous series between 0 and 1. Okay? Easy? Easy? This is a sigmoid function, y equals to mx plus c. In that case, y can have any continuous value, minus infinity to plus infinity. Y can have any value, right, between minus infinity to plus infinity. But our target variable, the target y is only 0 or 1. But if we use y equals to mx plus c, the prediction can be anything between minus infinity to plus infinity, and we cannot infer 0 or 1 out of minus infinity to plus infinity, right? So what we did, we transformed this y to sigmoid of y. We activated this equation with sigmoid function, and after applying the sigmoid function, we are going to get the results between 0 and 1. That is something we can use as a probability, right? Awesome. Okay, so we understood that y equals to mx plus c, y is going to have the values between minus infinity to plus infinity. Yes? Okay. The target variable is either 0 or 1. We cannot carry out the insight from minus infinity to plus infinity between 0 and 1, like either it's 0 or 1. If you are getting the results, anything between minus infinity to plus infinity, we cannot, we cannot carry out this information that it could be plus 1 or minus 1. Yes? What is the target variable here? In binary classification, we used to have two classes only, either 0 or 1. So target variable could be anything where we only have two classes, right? 0 or 1. Okay? Clear? Yes, guys, clear till here? This sigmoid thing is clear, everyone? The sigmoid of y is giving the result in the range between 0 and 1 only, right? Now from 0 and 1, we can easily understand whether it's like we can treat the sigmoid of y as a probability or as a likelihood, and based on that we can easily predict whether the outcome is 0 or 1. Yes? Yes, guys? Perfect. Now, how do we get the values of MNC? How do we get the values of MNC? For getting the values of MNC, there is the algorithm called MLE, maximum likelihood estimation. MLE, right? Stands for maximum likelihood estimation. Okay. Now, suppose if our actual y is 0 and predicted y, that is sigmoid of y, like whatever is the sigmoid of y, or wait, I should use predicted y, sigmoid y, or likelihood, right? It's not predicted y, it's likelihood, the probability, right? Let's suppose it's y, actual is 0, it could be 1, then likelihood, the probability, sigmoid y. For this, likelihood will be, I should not use sigmoid y here. For this, likelihood means chances of getting 0 will be 1 minus sigmoid of y, and this will be sigmoid of y. Yes? If it is 0, sigmoid y, the probability to get 1. If it is 0, 1 minus the probability to get 1. That's the likelihood. Right? That's the likelihood. The likelihood makes sense, everyone? Okay. So if we are calculating the sigmoid y, as the probability, right? So probability is the chances of event, right? Like whether we are going to get, let's take an example of disease. So sigmoid y will tell us with the probability of getting a disease, right? Sigmoid y will tell us the probability to get a disease, the probability that this person can have a disease. That's what the sigmoid y is going to get us. Yes, guys? Okay. So we understood what is sigmoid y. Sigmoid of y is clear, everyone? Sigmoid of y is the probability. How the probability will be 0.5? I'm sorry, how the probability is going to be 0.5? No, that means we have only two people, but that's not the case. That will not be the case. We have the huge amount of data and we want to calculate the probability that a patient is going to have a disease or not with respect to the other medical factors. That's what MNC, right? So sigmoid y will tell us on a given medical conditions whether a given patient is going to have a disease or not. The probability that this patient can have disease. Clear? Yes, is it clear? The sigmoid of y will tell us the probability to have a disease if the problem is detecting a disease or not, right? Okay. Yes, guys, is it clear? Perfect. So if there is a disease, if it is a disease, the sigmoid y should be maximum. The sigmoid y should be approximately equals to 1. And if there is not disease, this value should be approximately equals to 1. Yes, if the actually, like in the actual target, if the patient have the disease, sigmoid y should be approximately equals to 1, and if there is no disease, 1 minus sigmoid y should be approximately equals to 1. Yes, easy. Now this is clear. 1 minus sigmoid y and sigmoid y. Okay, suppose we have 70 patients without any disease, and I would say 27 patients with disease. Possible? In the actual data set, we have 70 students without any disease and 27 students with disease. Okay. Now, MLE, what maximum likelihood estimation will do, it will try to maximize 70 into 1 minus sigmoid of y plus 27 into sigmoid of y. This value will be maximized. This is what? The likelihood. This is what? This is the likelihood, right? And MLE will try to maximize this value in order to tune the values of M and C, right? And why we are actually maximizing it? To get more accurate predictions. Difference between sigmoid and MLE. MLE is an approach to get the parameters, the M's and the C, and sigmoid is a function, basically an activation function that will transform any continuous series between 0 and 1. Okay? Now this is how the values of M and C will be finalized. Maximum likelihood estimation, it will try to maximize the likelihood in order to get most accurate predictions. Make sense? Easy? Logistic regression? Easy? Yes, guys? Easy? So now the important question what can be raised here is during the interviews, difference between OLS and MLE, right? MLE, maximum likelihood estimation, is an approach to decide the values of M and C, while sigmoid function is an activation function that will transform any continuous series between 0 and 1. Okay? Right. So there could be a possible question during the interviews, that is what is the difference between MLE and OLS? Yes, guys? What is the difference between MLE and OLS? Ordinary least square and maximum likelihood estimation. In ordinary least square method, we try to minimize the sum of square of distances, but while in maximum likelihood estimation, we try to maximize the likelihood. That's the difference, and we can, derive these equations and all in order to explain. Got it, everyone? Yes, guys. Difference. Yes, difference between. Sorry. Difference between MLE and OLS. Maximum likelihood estimation is clear. What is maximum likelihood estimation? Everyone? Perfect. So we are trying to maximize the likelihood. And in OLS, ordinary least square method, that was the one we discussed in linear regression. What we were trying to do, minimize the sum of square of distances. That's the difference. Easy? In ordinary least square method, we try to minimize the sum of square of distances, but in maximum likelihood estimation method, we try to maximize the likelihood. Easy? Easy, guys? Awesome. Where do we use OLS? Yes, guys, anyone wants to answer? Where do we use OLS? Where do we use OLS? Anyone? Yes. Clear? Yeah. I think my neighbors are not happy with today. They are playing some sad songs. I don't know if you guys can also hear that or it's only me. Oh, that's actually nice. If you can't hear it, it's good. I was actually concerned about the voice. Yeah, that's good. That's I'm glad. I can't control the dogs. I'm so sorry. Yeah, those are all my friends. You assume that the people have same probability, right? But in general, we need to do each on separately. Right now, in this MLE approach, we try to estimate the values of M and C to maximize the probabilities, right? So that's why we want our M's and C in such a way that if the patient have a disease, the sigmoid y should be close to 1. If the patient do not have the disease, 1 minus sigmoid y should be close to 1, right? Okay, yes, what's your point? Okay, okay, I got you. I think you are talking about this multiplication of 70 or so. Yes, 70 into 27, right? Like I just put it for the explanation. I just put it for the explanation that yeah, that will be the sigmoid y is being calculated with the actual value of mx and mx plus c. I got you. This will be minus mx plus c. I just placed it for explanation how MLE works, but exactly it will try to calculate the 1 minus sigmoid y and sigmoid y for every value of x and c. Sorry, for every value of x. That is the medical factor of a given patient, right? So that 70 into or 27 into is basically just for the explanation what exactly MLE will try to maximize. But in actual, these 1 minus sigmoid y's will be calculated for all 70 patients separately for the given values of their x, right? Make sense? Clear, clear? Okay. Clear, guys? Logistic regression. We add up all the probability, right? I thought that must. No, we just need to maximize. Like overall, likelihood should be maximized. Ideally, the idea over here is we need to maximize the chances of occurrence. That if it is zero, the chances of having zero should be maximum. If it is one, the chances of having one is maximum. If we get into the actual algorithm, that actual equation, that has some log feature also included in it, log loss, some log likelihood and log loss, such kind of thing. But this is basically to explain how exactly maximum likelihood estimation works, right? Maximizing the chances of occurrence, maximizing the chances of occurrence. Correct? Perfect. Easy. Where will we use it? Anyone, guys? Where we will use it? Anyone wants to answer where we will use this? And where will we use logistic regression? Binary classification to predict the binary classification. Exactly. Got it? Where we will use? Got it? Where we will use the MLE? Awesome. Awesome. Perfect. Logistic regression is clear, guys? Awesome. Let's proceed to the next one. We have a lot of algorithms. Next is the KNN, and KNN is very easy. No nearest neighbor. Okay. No nearest neighbors. So let me just use an example. Suppose pulse rate and blood pressure. As logistic and linear different from categorical categories or same. Logistic regression is used whenever we have the binary classification problems, means we want to predict something in category and that has only two classes. That's where we use the logistic regression. Linear regression when we try to predict something in continuous, like sales or something like that. Okay. Suppose we have the data for the people having disease and not having disease. So it will give the class that has the more number of observations. If it is exactly between 0 and 1, it will predict for the one that has more number of classes, right? Majority. Then it will follow the democracy and it will say majority wins. Okay. Suppose this is the data set. We have the pulse rate and the blood pressure of the patients, and these rates are the people affected with some disease, and these green ones are the people that are healthy one. Now we have a new patient for which we only have the pulse rate and blood pressure. There is a new patient with some pulse rate and the blood pressure, and we don't know whether this patient is having some disease or not. So how we can calculate? We can simply plot the pulse rate and blood sugar. Let's say this is where the new patient lies. And the second case, this is where the new patient lies, right? So by observing the neighbors of this new patient, we can predict whether this patient have a disease or not. Easy? Now this can work with multi-class classification problems as well. Suppose there are three types of diseases, right? Healthy, disease 1, disease 2, or this also could be a possibility, right? So even if we have multi-class classification problem, this KNN algorithm would work, right? The new patient lies at here. It will observe the number of neighbors. Based on the neighbors, it will make the predictions. Now here, what exactly necessary? The number of neighbors we need to identify. How many neighbors we want to look? For suppose this is the new patient, I said 5. So we will check 5 neighbors. All the 5 belongs to red, so this prediction will be red. Here all the 5 belongs to green, the prediction will be green. Here the majority out of 5, let's say 1, 2, 3, 4, 5, right? So we can see 3 belongs to green, 2 belongs to blue. So this will be green, right? Right? So that's how multi-class classification can be done using no nearest neighbor, KNN algorithm. Easy? Yes. Which part? Yeah. What should I repeat? Which part is not clear? The KNN, no nearest neighbor, is the algorithm for multi-class classification problems. Means when we want to predict something that has lots of different classes, right? That has lots of different classes. What does green, red, blue groups indicate? Consider green belongs to disease A, or we can use anything. Let me again specify something. Let's say this is disease B, another type of disease. This is disease A, and then healthy patients. Possible? Possible? Got it? Circular region, sorry, where? There will not be any circular region or something. It will simply plot the training data. When we have the supervised machine learning, we used to have the target variable also. So we are going to plot the training data, and in training data, we will be having the target variable also, right? So based on the target variable, we plotted the observations with different colors, and when there will be a new observation, we will just observe its neighbor, and based on that we will predict that this observation belongs to that specific class only. Categories. It's right now all the algorithms what we will be discussing are classification algorithm. And when we talk about classification algorithm, it is category or a continuous. Clear? Awesome. So KNN is also easy, guys. KNN is also easy algorithm to implement. We say because this, but that are the input variables. Do we know the concept of input variables and the target variables? Yes, guys. Do we know the concept of predictors and the target variable? Okay, now whether a given problem is classification or regression, in order to decide that what we need to observe. The given problem is classification or regression, in order to decide what we observe. Target, target, right? Correct? Awesome. Is there any chance person having both the disease symptoms? How can we classify? See, the approach this algorithm is going to follow is by observing its neighbors, right? And at once, it will only predict one class. It cannot predict two classes at the same time, right? We cannot predict two classes at the same time. It will only predict the class one. Got it? We are getting intelligent. Awesome. That's why we are here, I think. Yes, guys? So we are going in a right direction, that means. Now? Perfect. Canon is also clear? Canon is also clear? Yes, guys? Everyone? Perfect. Now let's move to the next algorithm after KNN. Okay, we talked about KNN, we talked about logistic. Now I need to show some Excel sheets in order to understand what is this. Okay, sorry. In order to understand the third algorithm, that is Naive Bayes. Have we heard of conditional probability, anyone? Do we know anything about conditional probability? We know? No? In math? Yes. Yes. I think the probability was a subject in 10th or 11th something. In 10th standard or in 11th standard somewhere. The probability is a subject. In 12th, long back, yeah. And there used to be 5 marks question on conditional probability. Yes. Okay. Now, in order to understand, yes, it is. If one thing is true, what is the probability of next thing? Yeah, exactly. The questions in conditional probability were like that. If there is an insurance company, they have these many customers, and these many customers have met accident. Out of these many have claimed something. Now, if there are person of this age have met some accident, what is the probability that he is going to claim the insurance? These kind of questions, right? Awesome. So again, we are going to do some similar kind of things, right? Again, we are going to do some similar. Yeah, I'm from CBSE. We are going to do some similar kind of things here also. Let's observe this data set. What this data set explains, based on the outlook, temperature, humidity, and windy, some climate conditions, we are going to decide whether we should play or not, right? We are going to decide based on the climate conditions, based on the weather conditions, we should play or not. Now let's get the conditional probability into action. First of all, before we talk about the conditional probability, we note the probability of some event, chance occurrence of an event and non-occurrence of an event. So let's say probability to play, right, equals to number of times we have played, the frequency of play divided by total number of observations, right? Yes, that's how we calculate the simple probability. And this is going to be 9 by 14 as per this data set, right? Same examples. I'm honest, I don't know you, teacher. It's completely a coincidence. Okay, so here it's going to be 9 by 14, right? No, it's 14. It's 14, guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, it's 14. 9 by 14, right? Yeah. So this is the basic probability. Now, now, what if we want to calculate the probability of event Y given event X has already occurred, right? We need to calculate the probability of event Y given event X has already occurred. So, the formula will be probability of X when Y has already occurred into probability of Y divided by probability of X. That is the conditional probability formula, right? Right? That is the conditional probability formula, right? That's how we calculate the conditional probability. The probability of event Y if event X has already occurred. So how do we calculate it? The probability of event X if Y has already occurred into probability of Y divided by probability of X, right? So let's take an example. We want to calculate the probability to play if, let's use only one feature right now. If the outlook is rainy, if it's rainy, what is the probability to play if it's rainy? So how do we calculate probability to rain? The probability to rain when we were playing, right? Into probability to play divided by probability to rain, right? That's how we are going to calculate this. If we want to calculate what is the probability to play if it's raining, how do we calculate this? How we are going to calculate it? Probability to rain when we were playing multiplied by probability of play divided by probability to rain. Now let's see what is this value. How many times we have played? 1, 2, 3, 4, 5 and 6, right? 1, 2, 3, 4, 5, 6. 6 times we have played. Then we have played here. Then we are playing here. So in 9 times we are playing. Out of 9 times, only 3 times it rained. So this is going to be 3 by 9. Yes, guys. Probability to rain when we played is going to be 3 by 9 into 9 by 14 divided by 5 by 14, right? It's going to be 0.6. This is going to be 0.6, and the probability to play when it's raining, it's going to be 0.6. Easy? The conditional probability formula. Sir, 5. Okay, so out of 14 observations, 5 times it was raining. It's the probability to rain. How do we calculate the probability to rain? There are 5 instances of rainy out of 14 instances. So 5 by 14. Correct? Conditional probability. Yes? Everyone? As per this data, it's going to be 0.6. Okay. So if this thing is clear, we can move to next step. Awesome. Now, probability to play, if we have all the factors in consideration, means outlook, comma temperature, comma humidity, and windy. So how do we calculate this? Probability of whatever outlook is when we play it, right? Into probability of whatever the temperature is when we play it, probability of humidity when we play it, probability of windy when we play it, and probability to play divided by probability of outlook, probability of temperature, probability of humidity, and probability of windy. Right? We don't need to calculate it. We have the algorithms that will do all these things. We don't need to calculate. We have the algorithms that will perform all the calculations and they will give us the predictions. But we are just understanding how it's gonna work, right? So this is the conditional probability when we have multiple conditions, right? This is a conditional probability when we have multiple conditions. Make sense? And actually it is in the same way, like probability of y given x equals to probability of x, or given y, probability of y divided by probability of x. Now the x increases here, the number of x are many, four conditions have already occurred, so we are using px1y, px2y and so on, and then py divided by px1, px2, px3 and so on. Okay, so this is actually like this: p y, if we have x1, x2, xn, it will be probability x1 over y, sorry, probability x2 over y and so on, probability xn over y, probability of y divided by probability of x1, probability of x2, so on, probability till xn. Easy? Easy? So this is how the Naive Bayes, the algorithm, the name of the algorithm is Naive Bayes. So this formula is derived from Bayes theorem. This is called Bayes theorem. And why the algorithm is called Naive Bayes? If you observe all the input factors, outlook, temperature, humidity, windy, all the factors are given equal importance in order to calculate the target variable, right? It's naive. Yes, guys? But the one we discussed in, let's say, linear regression also, the input variables were having importances, right? The input variables were having importances, their impact, the beta coefficients. But if we see in Naive Bayes, every column is given equal importance. It's treating every feature as a naive. Make sense? Easy? Awesome, guys. Awesome. So Naive Bayes is also clear, everyone? Easy? The next algorithm is little interesting. Support vector machines. I'm sorry, Jana sir, was him. Does this depends on the data? So we need to extract, exactly, we need to extract the features. If we won't include the significant features, we might get some, false results. And honestly, these algorithms, this specific naive Bayes is not very widely used. In some use cases only that naive Bayes is fruitful, but it's not very widely used. What algorithm that is the most fruitful, and when like which one are the most popular classification algorithms? We'll talk about that. No, it can do for multi-class classification also. See, even if the play have multiple classes, then also this algorithm will work, right? If the target variable has multiple classes, then also this algorithm will work, right? So this can also work on multi-class classification algorithm, right? It can also work on multi-class classification problems. Yes? Understood, guys? Easy? The naive Bayes algorithm? Where to use KNN and naive Bayes. Basically, both are there are lots of other classification algorithms also. We see in naive Bayes, it strictly works on the probability, and this is going to get better results if the input variables are categories. But naive Bayes will be giving better results when the input variables are continuous, right? So like this, every algorithm is going to have its own features, its own methods to give the predictions. Right now, if we closely observe this naive Bayes algorithm, it works better with the categorical input features. It's not like it won't be working with the continuous input. It will also work with the continuous input variable. That is another form of naive Bayes, right? But it is more helpful when the inputs are categories. Okay, clear, guys, about the naive Bayes? That is not the only thing we need to observe while we pick while we pick the algorithm, guys, because again, there are very less hard and fast rules in real time solutions. What exactly we proceed? We prepare the data and we try multiple algorithms to get the solutions, and whichever algorithm gives the best accuracy, we pick that. So there are certain good to follow rules based on the data, how algorithms are working. We can get to know whether this can work on a given data set or not, right? So as of now, if we observe the formula and everything, we can say that naive Bayes can work better with with the categorical inputs, right? But now this is not a hard and fast rule that we have to use. We are only going to use naive Bayes if we have categorical inputs, and we cannot use naive Bayes if we have continuous inputs. So we can just make some good insights based on how algorithm is working, what data can suit for a specific algorithm. Though we have a lots of such exceptions, and whenever we get a problem, we try to solve it with different algorithms with different processing, lots of exploration, lots of trial and error thing, and that's how we came up with the final solution. Make sense? Yes, guys. Awesome. So naive Bayes is clear, everyone. By exploration, by doing a lot of attempts, by failing. Machine learning is what? Failing and improving, right? And that's how we also do. Perfect. Clear, guys? Clear, guys? All good till here? The three algorithms, three classification algorithms. Easy? Naive Bayes gives equal importance to the input features, but isn't significancy already incorporated in the probabilities? No. No. If the data, if the variable is not, it is actually utilizing the probability, right? But like, let's suppose in, the business terms, or in some, business understanding, there is some insignificant column, but this algorithm will try to extract some, information out of its probability as well. Make sense? From the domain understanding, there could be something that's not significant, but based on the statistics, based on the probability, there could be some some explanation in the probability of target variable. Possible? Yes, that could be a possibility. So significancy of selecting the input variables is important in case of naive Bayes. But lesser probability could also mean irrelevant variable. Okay, I can give you a small case. If we create this data without the windy variable, wait a sec. No, wind is something we use without temperature variable. Okay, these three columns give more better accuracy instead of using these four columns. You like when we will discuss the entropy and naive Bayes, sorry, entropy and decision trees, we will get to know that temperature is not actually helping in order to predict the target variable. That is the algorithm that is capable of ignoring the insignificant features by itself. But right now, if we give the temperature, these probabilities will also impact, right? If we calculate the probability to play on a given temperature, or if we include the temperature, their probability will be considered, right? Yes, their calculations will be placed in the formula, and that are going to change the overall predictions, right? Right? But the temperature is actually not impacting to target variable at all. How exactly it's not impacting? How exactly it's not impacting? We will understand this in like we will do SVM, and after that we will do a decision trees, and we will understand how temperature is not actually impacting. Okay, perfect. Understood why significance is important. We got the idea. We got the idea. Okay, perfect. Now, let me remove this and let's proceed to the support vector machines. Yes, guys, naive Bayes is clear, everyone? Naive Bayes is clear? Yes, guys, naive Bayes is clear to everyone. We can proceed to the next algorithm. Awesome. Perfect. Now we have third algorithm called support vector machines. So this algorithm work over vectors. I'm plotting the hyperplane first, and then I will plot the observations. Okay. Let's take the same example. Pulse rate and blood sugar level. Blood sugar. Okay. These patients, these people are having disease. These people are not having disease. Okay. These people are having disease. These people are not having disease. Right? And the support vector machine will try to look for a best fit hyperplane that can separate the classes. So how support vector machines will try to do the classification? It will look for the best hyperplane that can separate the classes at its best. Okay. Yes, now we will understand, we will see how to get this best fit hyperplane here. But how exactly support vector machine will do the classification? Is it clear? It will simply look for a hyperplane that can separate the two classes at its best, and that's how we will do the classification. How do we get the hyperplane? That is what we need to understand, and that is the training phase of support vector machines as well. So what exactly the criteria to do the classification? That is clear, everyone? A line or a hyperplane that's going to help us for separating the observation that belongs to two different classes. Easy? Okay. So we know the equation of line is y equals to mx plus c, right? Or it could be y equals to m1 x1 plus m2 x2 and so on plus c, right? Support vector machine are also classification algorithms, and right now we discussed how exactly they will perform the classification, right? No, not in vectors basically, because support vector machines can be used where we don't have the vectors as well. Sorry, they bark whenever someone passes by. Yeah. So this support vector machines can also be utilized where we don't have the vectors, any continuous variables, and we can also use them with the vectors. Why it's vector machines? Because the way they will, the way they train and the way they classify is with respect to the vector algebra, right? Their mechanics, their method, their mathematics is basically about the vector algebra. That's why they called support vector machines. They can be used for binary classification and multi-class classification also. Okay. The support vector machines can be used for multi-class classification as well and for the binary class as well. In the binary class, there will be only one hyperplane. In multi-class classification, there will be multiple hyperplanes to classify the different classes. So if suppose there is some third class, so there will be two hyperplanes in order to separate the three classes. So there will be a separate hyperplane to separate every class from other data set. Got it? Everyone? Yes, guys? Clear? It depends upon the number of classes we have. How many hyperplanes we can have, that depends on the number of classes, right? Clear? Okay. So we know the equation of a line. or I should not use y here because y we consider as a target variable. So let's not use this because here y is not a target variable. For this line there is no y. We can simply use ax plus by plus c equals to 0 as a as a straight line. Yes, this is also the equation of a straight line. Or again, let me not use by, let me use bx. Wait. Let me be more specific. Let's use a x1 plus b x2 plus c equals to 0, where x1 and x2 are the features like pulse rate and blood sugar. Yes, now this looks more correct. Got it? ax1 plus bx2 plus c equals to 0. That can be the equation of this best fit hyperplane that is classifying the observations, right? Yes, constant the intercept. Clear, guys? Perfect. Now, what if we create the matrices? Let's say I created a matrix W as A, B, and I create a matrix W, matrix X as x1, x2, right? We can create a matrix like this because that's how we represent a vector. We represent a vector in a matrix only. So we are actually trying to transform this equation into vectors, and we can simply create a vector W. We can simply create a vector W as A comma B, A and B, and a vector X as x1, x2. Clear? Yes? Clear, everyone? Okay. Now, as per this, here we see two intercepts. No, there is only one intercept, C. Yes, here we see only one intercept, C. A and B are the coefficient for x1 and x2, and there is a coefficient C. Right? Yes, clear? Yeah, using vector or using matrix, that's the same thing. The picture of blood pressure and pulse rate, there are two intercepts. Okay, so in that case also, no, there are not two intercepts. How we can say there are two intercepts? Like even if I write a equation as x or y, right? We saw this line y equals to mx plus c, right? So if we say the crossing of line is an intercept, so it is going to cross somewhere in x-axis also, right? It is going to cross somewhere on x-axis also. So this is not the intercept. Only this is the intercept, right? Perfect. Okay, now this is clear, guys. We have created a matrix W, or we can also say a vector W or a vector X with x1 and x2 and A and B. Clear? We have created vector W and vector X here. Got it? Now we can just write this equation as W transpose X plus C equals to 0. Yes? So now the equation of this hyperplane is W transpose X plus C equals to 0. Right? Yes, by the matrix multiplication. Yes, W transpose X plus C will be equals to 0. And we can simply say this is going to be the equation of this hyperplane. But the equation of plane contains three variables. This has x1 and x2. x1 and x2 is in vector x. They have coefficient a and b that is there in vector w. If we do w transpose x, we will get ax1 plus bx2 plus c equals to 0. Yes? Yes? If we do W transpose into X, what will be the result of W transpose into X, guys? What will be the result of W transpose into X? X1 plus Bx2. So I can simply write W transpose into X now plus C equals to 0. Right? Yes. Now suppose there is a equation of a hyperplane in 3 dimensions. I would say A1 x1 plus a2 x2 plus a3 x3 and so on an xn plus c equals to 0. That is also an equation of hyperplane in multi dimensions. In this case, we can also represent this equation as W transpose X plus C equals to 0, where W will be A1, A2 up to AN, and X is going to be X1, X2 up to Xn, right? And this equation can also be written as W transpose X plus C equals to 0. Yes? Now clear? The equation of a best fit hyperplane will be W transpose X plus C equals to 0. Yes, guys? Is it clear, everyone? Okay. Now, at this point, the W transpose X plus C is going to be greater than 0. And at this side, I can say W transpose X plus C is going to be less than 0. Right? Right? Lots of mathematics. Exactly, guys. Like when we used to do all these mathematics in our school days, so we used to think that why exactly we are doing all these things when it's like it's not helpful at all. We don't need these mathematics to buy vegetables, right? We don't need vector algebra to purchase vegetables or something. That's of no use. Of we used to think like that. Why exactly we are discussing the vectors and calculus, differentiation, integration, why it was there. But now it's actually that's going to give us salary, right? This that vector algebra, that calculus is going to give salaries now. Right. Okay. Now we understood this is the equation of a best fit hyperplane W transpose X plus C equals to 0. At one side it's greater than 0, at other side it's going to be less than 0, right? Right? Clear, everyone? Clear till here? Okay, now I can erase this multidimensional one. Perfect. Now we need to labelize the targets also. We need to labelize the targets also, the patients having disease and the patients that are not having disease. We need to give them some labels also, right? So ideally in the data set, it's usually 0 and 1. In the data set, it is either 0 and 1. 1 the people with disease and 0 with the people without disease, right? Right? That's what we used to have in the data. Got it? That's what we used to have in the data. But let's say this is a vector algebra. So we can make custom labels. These patients, let's say we are going to represent them as +1, and these patients we are going to represent them as -1, because the transpose vector is going to be less than 0. So all these patients, the label for all these patients are -1 and the label for all these patients are +1. Why we are not using 0 and 1? Because we are actually working with the vectors here. We are actually working with the vectors. So instead of using 0 and the 1 as a label, we are using +1 and -1. Okay, sounds good? Yes, guys? Sounds good? No, this, okay, it can be multi-class classification also, right? But right now we are working on the 2-class only. In the data set, it's going to be zeros and 1 only. In the data set, it is going to have 0 and 1 only. But for the training, for the calculation and all, let's make it +1 and -1. Okay, why we are doing it, we will get to know in a while. When we understand the mathematics, the equation derivation, we will get to know why we are actually, why we made it +1 and -1. So consider these observations are labeled as +1 and these observations are labeled as -1. Got it? Understood, everyone? Perfect. Now let's see how exactly we calculate the distance of a line from a point. So let's say this is a line ax1 plus, okay, now I'm using different notations. Suppose this is x-axis, this is y-axis, right? The equation of a line is ax plus by plus c, right? And there is a point x1 comma y1. Okay, we want to calculate the distance of line from this point, the perpendicular distance from the point. So the formula to calculate the distance is a x1 plus b y1 plus c divided by under root a square plus b square, right? That's the formula to calculate the distance. Yes. Now if we say the equation of line is w transpose x plus c, and here we have x1 equals to x1 y1, okay, right? And for this, w is a b and x is x y. Possible, the same thing what we have done here. In this case, the distance is going to be w transpose x1 plus c over norm of w, where norm of w is equals to under root a square plus b square. Same thing, we just represented the distance in terms of vectors, right? Yes? Same thing, we simply represented this equation in terms of vectors, and that's how we can calculate the distance. That is how we calculate the distance, right? Understood? Crystal clear? Yes, guys, what about this? Is it clear? Yes, it's the absolute. Thanks. Okay, so when we calculate the distance of a point from a straight line ax plus by plus c, where the coordinate of the point is x1 and y1, so we use this formula. Is it clear? This is the formula to calculate the distance of a point from a given line, right? Perfect. Now, if this ax plus by plus c we represent in vector form, that is w transpose x plus c, where w will be a b matrix and x will be xy matrix, and there is a x1 vector or x1 matrix that has the coordinates x1 and y1. So we can write the distance formula like this, where norm of w will be under root a square plus b square. Okay? Clear? Awesome. Now here is the interesting part. See guys, in order to get this best fit hyperplane, first of all, we need to basically, like, in order to get this best fit hyperplane, we need to maximize the minimum distance. Now, what does this maximizing minimum distance mean? There could be a hyperplane at this point of line. It's w transpose x1, and this is the coordinate of x1. This is the coordinate of x1. So this is w transpose x1 plus c, where these, like, whatever is xy, that is the coordinate of x1 and y1. So it won't be 0. Okay? In distance, it's not w transpose x plus c equals to 0. It's w transpose x1 plus c equals to 0. And what is this x1? The coordinate of x1 and y1. See here also, it was ax plus by plus c equals to 0. But here we placed ax1 plus by1 plus c equals to 0. Yes, that will also be 0 only. Okay, so if you are talking about this, w transpose x plus c will also be 0. Yes, that's true. So this is also w transpose x plus c is also 0 here. We can also write it as w transpose x plus c equals to 0. This will be 0. Okay? Clear? Perfect. Right. Now let's come to this point. Let's come to this point, guys. So in order to get the best fit line, we need to maximize the minimum distance from the hyperplane. So first of all, we need to find out the closest point. We need to find out the closest point. Yes, guys? We need to find out the closest point. And then we need to maximize the distance from the closest point to get a best fit hyperplane. So the distance, this and this, should be maximized to get this plane, right? This distance and this distance needs to be maximized to get this plane, right? Are we getting this part? That whatever distance is this, whatever distance is this, and whatever distance is this needs to be maximized. Then only we can say this is a best fit hyperplane. Let's say there is a hyperplane somewhere here, right? This is the hyperplane. So now this cannot be a best fit hyperplane because distances are not maximized in this hyperplane, right? Yes? So we need to maximize the distances, then only this hyperplane will get shifted and we will get a best fit hyperplane. Make sense? The point where both classes maximum distance intersect is the hyperplane. Exactly. The hyperplane has to be in middle, and to make the hyperplane, to have the hyperplane that is in between of both the classes, we need to maximize the distance both the sides. It should be maximized from both the sides. Then only it's going to be in middle. It needs to be maximized from both the sides. Then only it's going to be in middle, right? We can't say half or so, but it should be maximized, right? The overall concept, the overall, ideology here is to maximize the distance to get a best fit hyperplane. By same rate, sorry, by rate, you mean to say? By rate means by the same proportional distance. Uh, Sorry, see, we understand the distance. We understand the distance. Yes, guys, right? No, it has to be a line. I'll come to that part also. It can be curve or something. I'll also address this thing, how that is possible. We will talk about that also. That's called the kernel trick. We'll talk about that. But right now, let's see how this, if it's a line, how this will get in. We understand the distance, guys? Yes, guys? Is this distance is clear? Okay, you are talking about that. Yes, yes. It won't be actually in centimeters. We calculate it standardized by this sticks of x and y axis. That depends on the scale of x and y axis. Yeah, yeah, that's correct. That's correct. So we just need to maximize this distance. Is it clear, everyone? We'll address. Let's do one by one. Let's do one by one. What will happen if it's mixed? What will happen if we don't, we can't fit a straight line? We will talk about everything. But let's try to understand how we can train the straight line first. Okay? Let's do one by one, guys. Okay. Let's finish this. Let's finish support vector machines, then we'll take a break. Let's finish the support vector machines. So for having a best fit line, we need to maximize the minimum distances. Yes. The maximizing minimum distance. It is clear? Maximizing minimum distance. Is it clear, guys? Minimum distance, the distance from the closest point only. The distance from the closest point only, right? So we can simply write the equation best fit hyperplane beta h should be the maximum of minimum W transpose X plus C over norm of W. Okay? Yes? Make sense? Perfect. Perfect. Now, to make sure every observation is getting classified correctly, we will be doing beta h equals to maximum of minimum W transpose X plus C into Y over norm of W. Okay, now why exactly we are doing so? why we are multiplying it by y. Let's understand why exactly where we need to multiply it by y. But won't there will be a possibility to increase the classes distance to reduce the errors others. Possibility to increase a class distance to reduce others. I'm sorry, didn't get it. So let's say this is a class 1 plus 1, this is a class minus 1. So we need to maximize both the distance from both the classes. Yes? We need to maximize the distances from both the class. Increase one class distance to reduce others. No, why do we want to reduce other distance? Let's say if we are increasing this, why do we want to reduce this distance? That's what you want to say, like if we increase this distance, that's gonna get reduced. How do we get the maximum distance? How do we get to know? We don't want to know what is the distance, what is the unit of this. If we try to maximize at a certain point, the value will not increase, and that's where we will get the best fit hyperplane. We actually don't want what is the unit of this distance or what. We don't want the unit of this distance. We will keep on maximizing at a certain point, it will stop increasing, and that is where we get our best fit hyperplane, right? Make sense? In order to get a best fit hyperplane, okay, awesome, perfect. Now let's see, we are multiplying it with the target variable y. Why we are actually multiplying it with the target variable y? Suppose this is here W transpose X is going to be positive. W transpose X plus C is greater than 0, it's positive. Yes, guys? Y is also positive. Yes, Y is also positive. Positive into positive. Positive into positive. Positive. It's also negative. Y is negative. W transpose X plus C is greater than 0. It's also going to be negative. Negative into negative. Positive. Right? Right? Okay. Now, suppose there is some observation at this point. There is some observation at this point. So, by doing such multiplication, this will be a negative distance, right? After doing such multiplication, W transpose X into Y, this is going to be a negative, not from there. This is going to be a negative distance. This is going to be a negative distance, right? That needs to be gone at this side. Yes? By doing this, W transpose X plus C into Y, this is going to be a negative distance, right? Yes, this is going to be a negative distance. Okay, wait. At this side, W transpose X plus C will be greater than 0. At this side of hyperplane, W transpose X will be greater than 0. The target variable is -1, so this distance will be negative. And that's also because it's not in a right side of the hyperplane. At this side of the hyperplane, W transpose X plus C is positive. But if there is a green observation at this point, which label is -1, so that distance is going to be negative. This value is going to be negative, right? right? Yes? Yes, exactly. So to make sure the hyperplane is being created in such a way that all the observations are getting classified correctly. To make sure, to make sure all the observations are being classified at a right side of the hyperplane, we are creating this hyperplane, right? Why we multiplied it by y? To make sure all the observations are being classified correctly, because if there is some observation at this point, this is not right and this would have a negative distance in that case. Makes sense? This is going to have a negative distance in that case. Yes, guys? So that's why W transpose X plus C is multiplied by either plus 1 or minus 1. That is the actual label of the target variable. Difficult to understand? No problem. Is it clear that this side of the hyperplane W transpose X plus C is going to be greater than 0? Yes? Okay. If there is a green observation at this side, the label of this green observation is minus 1. Yes? And if we try to calculate W transpose X plus C into Y, because we had already discussed the label of the green observation is minus 1 and the label of red observation is plus 1. That, yes guys, we had discussed this thing. We had talked about this thing that the label of these observations are plus 1 and the label of these observations are minus 1. Okay. Now, the label of this observation is minus 1. So, when we calculate W transpose X plus C into Y, it will calculate this distance as negative. And why this is negative distance? Because this is not at the right side of a hyperplane. Yes? Got it? Yeah. Understood? Okay. Now this is actually not a mod, because we calculate mod when we don't have the direction in consideration. We use mod. We use mod when we like this, either it's this or this is not a point. Like this is not a concern whether we are calculating this direction or this direction, but when this direction of the distance is something that needs to be considered, we don't use mod in that case. We don't use absolute value in that case, right? If the distance of the direction needs to be considered, we won't be using the absolute value in that case, the absolute value of W transpose X plus C, right? Here it was absolute because we just want to have a distance, the magnitude of the distance. But when the direction of the distance is also important, we won't be using the absolute value, right? Make sense? Yes, this makes sense, guys. Perfect. What did the end goal of this algo? The classification. Yes. Okay. Clear, guys? Okay. Now this is the equation. This is the equation that's going to get the best fit hyperplane. This is the equation that is going to get us the best fit hyperplane. Clear, everyone? If we need to maximize this, we need to optimize the norm of W, and that is our overall goal. We just need to optimize the norm of W to get the best fit hyperplane. Okay. Lots of mathematics. Yeah, now we can have a break. Okay, now after the break, we will talk about the further use cases. What will happen if the data is not linearly separable, or what will happen if a straight line or a linear hyperplane is not able to separate the classes. So we will talk about those concepts, those possible use cases after the break. Okay, perfect, guys. Let's take a break. Let's take a break. Definitely, we get the questions in interview on the concepts part only. No one will ask you about the code or something. We will only get the interviews from the concepts. Okay. Yes, you need to be very sure, very confident about every algorithm, how exactly it's working. – 20 minutes. Yeah. Let's get back after the break, guys. Everyone, we are all back now. Awesome. Awesome. Okay, so what we did, yes, we understood how do we get the best fit hyperplane. Now, what if the data is not linearly separable, or what if the straight line is not possible between the data set, right? That's what we were trying to discuss. Yes, guys? So in that case, there is a concept in support vector machines called kernel trick. What happens in a kernel trick? Like we know, a straight hyperplane can be there, and a curved hyperplane can also be there. Yes, this is linear, and this is polynomial, right? A straight hyperplane is possible, and a curved hyperplane is also possible, right? As per the requirement. So either we can give polynomial hyperplane or the linear hyperplane. But what if data is not separable at all? I would say if the data is like this. Right? What if the data is scattered like this? Yes, what if the data is scattered like this? Now, what will happen? We can't have the enclosed hyperplane, means there could not be a circle here. So what we do, let me show you what we do in this case. Got it? The linear and polynomial is clear, everyone? Yes, guys, the linear and polynomial is clear? Okay. Now, if we have the data scattered like this, what we do? Let me show you. Kernel trick SVM. See. Yeah. Exactly. We project this data to another dimension, the third dimension. This one. Suppose this is x, this is x1, this is x2, right? x1, x2, x1 and x2 are there, but the data is not separable at x1 and x2. It will create a third dimension, x1 square plus x2 square, right? x1 square plus x2 square at this third dimension to a higher dimension. Now we can see the data is separable with the decision surface, right? This is called RBF kernel, radial bias function. This is called RBF kernel, radial bias function. Okay. So this is what happens in the new dimension. This is what happens when the data is not separable, right? There were some questions during, like there were some questions during when we were trying to understand the minimizing the maximum distance. So few learners were confused about what will happen if the data is not separable. So in that case, we make the data into higher dimensional, and that's how data can be transformed to a space where there is where data can be separated, right? Make sense? Yes, guys. So there are three possible kernels: linear, polynomial, and RBF. Right? Linear, polynomial, and RBF. This is the RBF. Yes, this is on the third dimension, that is x1 square plus x2 square. On this dimension, the data is separated. And this is the third kernel, that is RBF. Polynomial is also possible and linear is also possible. Right? And if I talk about where exactly this kernel thing is implemented in the equation, maximizing the minimum distance W transpose here, it calculates the phi of x plus c into y divided by norm of W, right? Where phi is the kernel function. If you try to look at the research paper of support vector machines, the researchers, the developers who have proposed these techniques, this is what exact algorithm, exact equation would be written there. And this phi is the kernel functions, because it's going to be a linear or it's going to be a polynomial, that completely is the game of dimensions, right? Yes, guys? It's going to be a linear surface or a polynomial surface or a RBF surface. That completely depends upon the dimensions, the x vector here. So that's why the kernel functions will be applied. The kernel function will be applied to the vector x in order to get the data classified correctly. Yes. So if you try to look at the exact research paper of support vector machines, this is what we will find. Got it? Got it? About the different types of kernels in support vector machines, guys? Everyone? Perfect. Interesting? Interesting? Yes, linear, poly, RBF, these are also the kernels. Yes, we are creating a new feature, that is x1 square plus x2 square. So there are three possible kernels: linear, polynomial, or RBF, radial bias functions, and we can use the kernels as per the requirement. Yes, guys, understood? Yes, we just, like when we want to create a support vector machines, we just need to give we just need to give which kernel we want to use while we create, when we will be doing the code, we will just tell we want the RBF kernel. By default, it always creates a RBF only, but if we want to use linear or polynomial, we can just simply use that linear or polynomial. We can simply give linear, poly, and the code, the library will do everything. Okay, the code, the library, sklearn library will do everything. Correct? Awesome, guys. Interesting support vector machines. Now they are very much capable. One of the practical implementation of support vector machines are face recognition and face detection. But now we have more advanced and more, better algorithms to do the same thing. But once support vector machines were the algorithms that stand out, they outperformed in face detection and face recognition cases. Understood everyone about the support vector machines? Easy? Easy? When the linear or polynomial should be used? As per the data distribution. If the data is separable with the linear kernel, with the linear hyperplane, we can use linear. If it can be separated with a curve, we can use polynomial curve. Is there a book for theory? I have shared a link. I have shared a book, a link from O'Reilly. Oh, really? Yes. Yes. Oh, really? Yeah, that's the name. Hands-on machine learning. Sure. No, it's not there. It's not there. This book, guys, this book, I think we have talked about this book 3, 4 times now. You can refer to this book. Okay? Hands-on machine learning with scikit-learn, Keras, and TensorFlow. You can you can easily get it somewhere. I personally don't have the PDF version of this, but if you will try to search, you will get it somewhere. Or you can like, if I would suggest just get the hard copy of it, because when it comes to the book, guys, when it comes to the book, the reading the PDF version of the books is, I don't think it's, that much. It will not. I don't know. I like the books. I like to use the hard copy when it comes to the book. Until you will use some pen and you'll start scribbling. You'll start scribbling over the book. So until then, it doesn't seem like we are reading a book, right? So whenever it comes to a book, I would suggest use a hard copy, guys. Because when we try to study the digital copy on smartphones, like definitely if we are downloading a PDF version, we are going to read it or we are going to study on phones, and phone have a lot of distraction. Yes, it's a trap. You can't study on phones. You can't, yeah, exactly. You can't study on phones. I would suggest, guys, just if you actually want to read the book, just order the hard copy of it and go through with that. And if you are okay with the digital version as well, if you are okay with the digital version, it's completely up to you guys. It's subjective opinion. It's completely subjective opinion. So whatever you feel is good, you can go with that. Yes, new generation, digital notes. Okay, awesome. We can proceed with the next algorithm, guys. Perfect. So now we don't need the whiteboard anymore, and I think there is no space left. No space is left. Okay, but we need Excel now on the same data set. Okay, now the next algorithm is decision trees. The next algorithm what we will be discussing are decision trees. Okay, now before we talk about how these trees are trained, how we get these decision trees, let's see the end result. What will be the end result of a decision tree? So there is a data. Let me divide the data with respect to the outlook. Okay, so in outlook we have overcast, rainy, and sunny, right? This was on outlook. Yes. Now in overcast we are playing, and we can terminate the tree right here. In rainy, rainy, we need to check windy. Check windy. False or true. So if it's false in rainy, if it is false, we are playing yes. And if it is true, we are not playing at all. That's the termination of the tree. In sunny, I think we are checking the humidity or windy. In sunny, we are checking the humidity. It's going to be high or normal. If it's high or normal, if it is high, we are not going to play, and if it's normal, we are going to play. Okay, now we can see this tree is going to classify our this data. If you pick any random row, and if we follow this decision tree, we will get the right prediction. It's rainy, rainy. Now check the windy, windy is true. Rainy, windy, true. We are not going to play, and that's the prediction, right? Yes. So decision tree will build this tree. The decision tree will try to build this tree. Okay, we got the PDF, guys. We can save if we want the PDF. Yes, guys. The decision tree will create such tree, and if we follow the decisions, we are actually getting the right predictions. Yes, guys. Yes, this tree makes sense, everyone. We have a tree here, and see, let's pick any random row. Let's pick any random row, guys. So just pick any random row. Let's say this. So first, it's overcast. We need to observe the outlook at the very first. It's overcast. We observed overcast, and we can say we are playing, and we are correct, right? Row number 12. Uh, the outlook is sunny. The outlook is sunny, right? So we are at this branch. Now after sunny, observe the humidity. In sunny, what is the humidity? High. Humidity is high. We are not playing, and we can see the prediction is no, right? So this tree is clear, everyone? Thirteenth row? I don't think so. 13th is contradicting. It's fine. Perfect. Okay. Now we need to understand. We need to understand how this tree. What is the use of this tree? Basically, this tree can help us with the predictions. See, suppose if we don't have this, based on this data, if we only have these 4 records, we can easily make the predictions whether we can play or not. Right? We can easily we can easily make the predictions whether we can play or not. Now what we need to understand in this, we need to understand how exactly we got to know that we need to look for the outlook first, then we need to look for humidity, or we need to look for windy. How exactly we decided this split, right? Here is a split on outlook. After rainy, there is a split on windy. After sunny, there is a split on humidity. How exactly we are going to decide the split? That's the question, right? That's the big question. How do we get to know that we need to look outlook first, and we need to use windy second, and then we need to check for the humidity if sunny is the outlook. That is the question. How do we got to know about the split here, right? And that is something we get at the training state. Okay, that is something we get while training. No, not random forest. It's decision tree. Okay, understood the decision tree, guys? This approach is clear, and what is required, what we need to understand, we need to understand how this training will happen. How do we decide the split, right? Okay, now we got what exactly is decision tree, how decision trees are going to make the predictions, and how they are going to be helpful. Yes? We are creating a tree based on the decisions, and if we follow those decisions, if we follow those tree, we are going to get the predictions, the desired predictions. Clear, everyone? Yes, clear, everyone? Okay, now before we talk about its technical aspects, that means what exactly is entropy and other things. Let's try to understand some basic terminologies here. So one thing is called degree of randomness. Have you heard of this term, degree of randomness, ever? Yes. Yeah, entropy, degree of randomness. Now, what do we understand by degree of randomness? How random the decision is, right? How random the decision is. And if the degree of randomness is high, the degree of randomness is high means we are taking less calculated decision. The chances of that decision to be correct is less, right? Yes, guys. For example, we try to make some decision. If we make very calculated decision, then the degree of randomness will be less. Means chances of that decision to be to be incorrect, to be an incorrect decision will be less, right? Yes, guys. That is the concept of degree of randomness. Degree of randomness means how calculated our decision is. If it is more calculated, the degree of randomness will be less. Yes, degree of randomness should be less. If there are more chances to get to make a incorrect decision, then there is degree of randomness high. Okay. Understood? So if we can take any example, right? So if we want to do something, we take a decision to achieve something, and whether that decision was correct or not, that will be decided by the degree of randomness. Lesser is the degree of randomness, better is the accuracy. Exactly. Suppose uh, anything we want to, we want to upgrade, we want to get a better job, we want to upgrade, we took a decision to go for a data science course, right? So what is degree of randomness here? The degree of randomness is very less because we took a calculated decision to opt for a data science course in order to upgrade our career. Yes, this example should make sense. So yes, guys. So degree of randomness is less. We have more chances to get our decisions correct. If the degree of randomness is high, there are more chances that we are making an incorrect decision. Make sense? The degree of randomness is clear, everyone? Less randomness, more accurate. Okay. Now let's come to the point. How do we calculate the degree of randomness using entropy? Excuse me. Excuse me, it's unknown, so it could be someone important. Okay. Sorry about that. The number showed on screen. It was a delivery, guys. Okay. So we calculate the degree of randomness as entropy. And the formula to calculate the entropy is minus P log P minus Q log Q. Right? Where P is the probability of occurrence and Q is the probability of non-occurrence. P is the probability of occurrence and Q is the probability of non-occurrence, right? Clear? Yes, guys, clear? Everyone? Great. Now, we need to calculate the entropy of play for every column outlook, right? We need to calculate the entropy of play for every column. Let's say first we will calculate for outlook. What will be the entropy? Probability of having overcast into entropy at 1, 0 plus probability of rainy into entropy of 0.6, 0.4 plus probability of sunny into entropy at 0.4, 0.6. Now from where this 1, 0 came, see, in overcast, probability to play is 1 and probability not to play is 0, right? Probability to play is 1 and probability not to play is 0. Yes? Similarly, in rainy, probability to play is 3 by 5. That is 0.6. Probability to play is 3 by 5. That is 0.6. Right? 0.6. And probability not to play is 0.4 in rainy. Yes? Similarly, we can calculate in sunny. Right? And that's the probability of sunny into entropy at 0.4, 0.6. We will expand this formula. How will we expand it? So probability of play is 4 by 14 into -1 log 1 minus 0 log 0 plus 5 by 14 into minus 0.6 log 0.6 minus 0.4 log 0.4 and so on. Like, we can expand this formula and we can calculate this value, right? We can expand the formula and we can calculate this value. We understood the approach. How do we calculate the entropy, right? Yes, guys? Understood? Or should I write the entire formula? Is it clear, or should I write the entire formula? Let me make some space. Clear? We understood? We can expand it and we can calculate the entropy at outlook. And now what will be this value? It will be the degree of randomness at outlook. Similarly, we will calculate the degree of randomness at temperature, humidity and windy. Whichsoever column will have the least degree of randomness will be used as a first split, right? Whichsoever column is going to have the least degree of randomness will be treated as a first split. Clear? Now, after we have a split, after we got the first split, then we will be having the different subsets of the data, right? Then we have 3 such data sets after the split. Suppose we will be splitting on Outlook. So after doing the split on Outlook, we will be having 3 different data sets. Yes, 3 branches of the tree. This will decrease the wideness of the tree and increase the depth. Yes, yes. but yeah, this is actually not a problem. We can have the huge depth of the tree. That is okay. The number of branches, we don't actually require a huge amount of branches in the beginning, right? Perfect. Yes, guys. Understood. Now we decided the initial split based on this entropy and everything, and we will create three different branches of the tree. Yes, guys. Yes, awesome. Now, after doing the split, we are going to have three subsets of data. The same thing will be applied on these three subsets on temperature, humidity, and windy column, and their further splits will be decided, right? Outlook is done. Suppose we have split it on Outlook. It's done. It's not required anymore. So we will be having these three subsets. The same thing will be applied on these three subsets on remaining columns, and that's how it will decide the further splits. Okay? And remember the tree what we built in the beginning. The temperature was not utilized at all. Remember the tree what we were building in the beginning. The temperature was not utilized at all. And that's what I was trying to say at the time of naive Bayes, that temperature is not going to help in order to make the right predictions. These three columns are enough, right? In that tree, the three columns were perfectly classifying the data set, even without utilizing the temperature. So if we also use the temperature in naive Bayes, definitely it is going to add some noise, right? Make sense? So, and if we see, the naive Bayes was also variation of probability theorem, probability concept, and this is also a specific variation of probability. Here also we are completely working over the probability concept. Yes? The outlook will be used as a first tree because here we have calculated the entropy for outlook. If we will, so we understood the formula. How do we calculate the entropy of outlook? If I remove this half expansion, we understood the formula, right? Same way we can calculate the entropy for all the four columns, right? So if we will calculate it, outlook is going to have the least entropy. That's why outlook is being utilized at the first. Okay, so we calculate the entropy as minus P log P minus Q log Q. That is the entropy. See, we calculate the entropy for all the columns, and the outlook column is going to have the least entropy. That's why we used this column for the initial split. Clear? How we are calculating the entropy? The formula is minus P log P minus Q log Q. Okay? The formula is minus P log P minus Q log Q. That's the formula. So if the outlook has three categories, one is the overcast. So we calculated the probability of overcast into entropy at overcast. 1 0, the probability of play yes is 1 and the probability not to play is 0 here. Yes, if you see in overcast, the probability to play is 1 and the probability not to play is 0. So that's why we will be calculating entropy at 1 0. Right? Plus probability of rainy. What will be the probability of rainy into entropy at rainy? So probability to play in rainy is 0.6 and 0.4. That will be PQ for entropy at rainy plus probability at sunny into entropy at sunny. That will be 0.4, 0.6. Right? This way we can calculate the degree of randomness to play if we know the outlook. Yes, guys, this way we can calculate the degree of randomness to play if we know the outlook. Yes, guys. Awesome. Now We can calculate the degree of randomness for all the columns. If anyone is missing, if there is any missing value, then we need to deal with the missing values first, right? So these algorithms and training, everything we do after we prepare the data set. Yes, yes. So this is how this is how the decision tree is going to work. Easy? Yes, guys, easy. This is how the decision tree is going to work. Understood? Perfect. Perfect. Okay. Now this is a small data set and we can easily conclude the tree. Think of an example where we have hundreds of columns. So till what point the tree should keep on splitting? Yes, suppose we have hundreds of columns. So till what point the tree should keep on splitting? Anyone? Suppose we have hundreds of columns here. So till what point the tree should keep on splitting? And right now in this example itself, the tree removed one column for the split. Till the branches have end result. Yes, till the leaf node is having zero entropy, means 0 degree of randomness. Till the root node, the leaf node where the tree is getting terminated is having zero entropy, right? Ideally, that should be the right approach to keep on splitting. The tree should keep on splitting until the root node, or not root node, the terminal node, right? Yes, guys, the terminal node is having zero entropy, right? The terminal node, the leaf node is having zero entropy. We need to keep on splitting till then. Make sense? I'm glad, guys, we are getting intelligent. Perfect. Understood? When we should keep, till when this decision tree should keep on splitting. Now, once we understood the split criteria, let's talk about its problem. Is this thing is clear, everyone? The decision tree, how it will decide the split and till when it should split. Is it clear, everyone? Awesome. Awesome. Now let's talk about a specific use case. Let's say there is a tree, right? Multiple branches. Okay, there are multiple branches. Suppose at a certain branch, right? There is further split. Suppose at a certain branch, we have 10 observations, right? In this branch, only 10 observations are left, right? In this branch, only 10 observations are left, where 9 belongs to one class and 1 belongs to class 0, right? 9 belongs to class 1 and 1 observation belongs to class 0. They belongs to 1 and 1 belongs to 0. Possible? Out of these 10 observation, 9 observation they belong to class 1 and 1 observation belongs to class 0. Possible? At certain instance. So if we keep on splitting until entropy becomes 0, it will add one more split for 9 and for 1, right? And we can see this is the case of overfitting. Yes, we are making a split, we are adding a split in the tree just for classifying one observation. Overfitting. Yes. So splitting until entropy 0 is good, but this will make these decision trees more sensitive for overfitting. Make sense? Make sense, guys? This will make decision trees more sensitive for overfitting. Now, what is the solution? We can limit the depth, right? We can limit the depth. We can limit the depth. Specify we should not split the tree more than these many times. We can limit the depth, right? We can have, like we can say, the terminals, the leaf node should have at least 5 observations. Some minimum number of observation we want to have in the leaf node. That will also restrict the unnecessary splits. This is called max depth, right? This is called minimum sample in leaf node. Minimum sample leaf. Let's say we are telling in the leaf node there should be at least 5 samples. If we are saying in the leaf node of the tree there should be at least 5 samples, we should not create a split only for one sample, right? That means if there is a split, that split should have at least 5 samples. So if we specify these terms also, it will not allow the tree to make these kind of splits, because the terminal node here is having only one observation, and we said the terminal should have at least 5. So the split will not happen. Make sense? Not each split, not each split. The leaf, the terminal node, the leaf node, where the tree is ending, that node should have at least given number of observations. Yes? Every terminal node, the last node where we are terminating the tree, at least some, now this 5 needs not to be very static. We can change this number, right? But we can specify some minimum threshold to avoid the overfitting. So the maximum number of branches and the minimum number of sample can be limited. They can be limited, right? In order to deal with the overfitting scenario in decision trees. That can be limited. That is something we can specify in order to deal with the overfitting. Okay? Perfect. Perfect. Got the idea of decision trees, guys? What are the pros and cons of decision tree? Like they can get easily overfitted, but there is a solution to deal with the overfitting. Sure. That also makes sense. That also makes sense. So yeah, we can stop at this point. Tomorrow there is one thing left. The ensemble learning means how we can combine the decision trees to get more better accuracy, and then we will do the code. Okay? Yes. The ensemble learning and the code will be the agenda for tomorrow. Anyone, any questions? Anything? Yeah, please, you can ask questions. What do you suggest about revision? Go through with the concepts. As of now, we don't have the code right now to do but I would say just go through with the concepts part, or try to read more about these things. Do we need to check if the data is normally distributed before applying linear regression? Ideally, it is said that linear regression has these prerequisites to have the data normally distributed, but in real time, we cannot have the real world data normally distributed. So it's good to check, and it's also good to perform some transformation to make it somewhat normally distributed. But again, it's not very mandatory. Do sklearn also check significancy of each column? Not like this p-value or something. Sklearn cannot give the p-value or so, but sklearn can give the magnitudes, and based on those magnitudes, we can have some idea about the significancy. Once OLS done, can we remove insignificant columns? Exactly. Definitely we can remove and we can retrain the OLS. Yes, we can try that. All population don't have linearity relationship. Are we covering polynomial regression in this course? In polynomial regression, there is nothing different than linear regression. Just the features what we have x, x1, x2, we can have some degree, some polynomial term of those features. Let's say you have the advertisement amount to predict the sales. If the advertisement amount is not having a linear relationship, you use advertisement amount square to predict the sales, and that is the polynomial regression, right? Make sense? Then without plotting, can sklearn tells the population is not linear? No, in order to check the linear, in order to check the okay, it's not linear. No, we cannot check. We cannot check whether it's linear, there is a linear relationship or not without plotting out this. There is a test that is not again for checking linearity, that is for checking the data distribution, Durbin-Watson test of normal distribution. If anyone have heard of this, there is a test called Durbin-Watson test that can check the normality in the data set. Okay. Yeah, so we can use that to check the data distribution. Perfect. Anything else? I hope everything is clear. Definitely. Like what exactly we are referring to plotting here? That is, plotting is good before applying algo. It is actually doing EDA before applying algo, doing exploratory data analytics before applying algorithm. And in EDA, we try to understand these things only. The data, whether the data is correlated, significancy, multicollinearity, it's distributions, value counts, mean, median, mode, all these things. That's what we try to understand in EDA, right? So definitely we do exploratory data analytics before we build model. Yeah, please, if there were any questions, sorry, I forgot to address. Make sure we are placing the questions to all participants, so everyone should be aware of what we are exactly discussing. Perfect. Understood, guys? Understood, everyone? Let me know if anyone have anything. We just need to make sure we do revision. We try to read more about these mathematical and algorithmic concepts. Definitely we are limited with time, but we tried to we tried to get into as much as possible depth of each and every algorithm, be it mathematical aspect or its conceptual aspect. We try to touch the maximum depth of every algorithm, and we need to keep on exploring the different methods and all possible information about these algorithms. If someone is more interested, you can actually go through with the research papers. You will get each and every detailed explanation about every algorithm. You can definitely explore their research paper. IEEE is there, and IEEE website where you can get all the research papers. Plus, there is also website, I'll tell you tomorrow, where we get the codes plus research papers of these kind of things. I think, just a sec. Yeah, GitHub is there, but if you want to explore about the research papers, there is a website, paper with codes, research paper with code, some website by the name like this is helpful in exploring in-depth concepts. Paper with code. There is a website, papers with code. So just search papers with code that have the codes and the research papers of different projects, different tools, also the algorithms. Papers with code, latest in machine learning. So this is also helpful. This is also helpful. You want to explore support vector machines. So it will have all the research papers for support vector machines along with their codes, right? But this is going to be the extreme technical aspect of the algorithm, right? If anyone is interested in exploring the extreme depth of every algorithm, you can definitely explore the research papers, right? And actually, this will require some mathematical and programming background. This will also require some mathematical and programming background. Sounds great? Perfect. If there is nothing, we can conclude the session. Thank you, everyone. Thank you all. See you tomorrow. We'll be doing the codes and ensemble learning. And yeah, that's it. Thank you, guys. Bye bye. Take care. Stay safe. Stay happy. Stay healthy. See you tomorrow. Bye bye.
Thank you, sir, for this wonderful session, and thank you all for your participation. I request everyone to kindly fill the feedback survey form and share your comments regarding today's session. I've already shared the link in the chat box. Please do fill the feedback survey form. Take care, everyone. Thank you.